All right, we're going to talk about limit of a function and limit laws. This is going to be kind of part one. There's going to be a second part. So here I have my function. F of x equals x squared minus 1 over x minus 1. How does this function behave at x equals 1? Well, we know that we can't plug in 1 here because then we'd have a 0 in our denominator. So the first thing I want you to do is I want to kind of look at what happens is when I get really close to 1. So we're going to start by plugging in 0.9 into this and just kind of see. So I'm going to take 0.9 squared minus 1 divided by 0.9 minus 1. And this is going to give me 1.9. So this is 1.9. All right. Now I'm going to take 0.99 and I'm going to do the same thing. So 0.99 squared minus 1 equals, and then divide that by 0.99 minus 1, and that's going to give me 1.99. And you might start seeing a pattern here. If I plug in 0.999, I'm going to get 1.999. Now we can't plug in 1, so I'm actually going to start at 1.1 and then work backwards because it's farther away. So if I plug in 1.1, square it, minus 1 divided by 1.1 minus 1 is going to give me 2.1. So this is going to give me 2.1. And then if I put in 1.01 squared minus 1 equals divided by 0.01, that's going to give me 2.01. And if I put in 1.001, that's going to give me 2.001. So you kind of see a pattern here. And if we look at this, we notice that values that are under are going to approach the value of 2, and values that are slightly over are approaching the value of 2. So what would our function behave at 1? We're looking at, yes, we can't plug it in, but where are these y values converging on? And the answer is 2. So if we look at this algebraically, we can look at this and go, well, I know that x squared minus 1 can be factored. And it can be factored into x plus 1 and x minus 1 over x minus 1. Well, then if I cancel these out, I'm left with x plus 1. Now, x plus 1, I can actually plug 1 in and get that 2. Okay? Even though our original function, I could not. So that's kind of that looking at that behavior at a certain point. So the limit of f of x as x approaches c is L. So what this is essentially saying is values of f of x are close to the number L whenever x is close to c, okay, and on either side. So notice here, values that were slightly below, I was getting close to 2. Values slightly above, I was getting close to 2. Okay? Now, we're going to kind of look at this one here. So here I have two piecewise functions. And I'm going to look at each of these. And I'm going to come over here, and I'm going to graph this first one, this u of x. That way we can have a visual representation of it. All right? So here's my graph, 1, 2, 1, 2, 3, 3. And it says I'm at 0 when x is less than 0. So I'm going to come up here, put my circle, and I have this line right here, okay? And I'm at 1 when x is greater than 0. Now, on our graph, when we look at this, if I'm looking at what happens when this approaches 0, so on both of these, I'm looking at what happens when I approach 0. So if I'm values less than 0, so I'm approaching from this side, coming on this side, I actually end up showing that I have a value of 0, right? Because all the values left of it are at 0. And all the values on the right side of it are 1. So here we have what we call a jump, so to speak. So we're jumping from 0 to 1. So we don't have any limit there. We can't say, oh yes, this is going to behave in this manner. On both sides of it, whether I'm greater than or less than, I'm approaching the same value. I didn't approach the same value, so therefore I don't have a limit there. Now we're going to look at this graph here of 1 over x. So if I look at this, I end up with a graph that is similar to this here. And then I have a graph here. But it says at x equals 0, I have this point right here. So I am defined at 0, right? But let's look at what happens when I approach from each side of 0. So if I approach on values left or less than, I'm coming along this curve here. And which, oops, put this backwards. Sorry, put that backwards for some reason. That's like negative 1 over x. Okay, so as I'm traveling along here, as I get values that are closer and closer to 0, this is actually going towards negative infinity, right? And if I come from the right, if I'm traveling along this path here, I'm going towards positive infinity. So even though I'm defined at 0, I don't have a limit because the left side, values less than is going to negative infinity, and values to the right are going to positive infinity. All right? So now we're going to talk about kind of our limit laws. And this is kind of where we're going to look at a lot of information here. So limit laws are if the limit as x approaches c equals L, and the limit of g of x as x approaches c is equal to n. So we have the sum. So let's say the limit as x approaches c of f of x plus g of x, that's going to be the sum of the limits. So L plus n. The difference of the limit of f of x minus g of x as x goes to c is the difference of the limits. So L minus n. If I multiply by a constant, I'm going to multiply the limit by a constant. If I multiply in here, the limit of f of x, g of x, as x goes to c, is going to be the product of the limits. The limit of L over times n. The quotient is going to be the quotient of the limits, but n cannot equal 0. The power, so the limit of as x goes to c of f of x to the nth power is going to be the limit to the nth power, where n is a positive integer, okay, or a natural number. So the root, the limit as x goes to c of the nth root of f of x is going to be the nth root of the limit, or L to the 1 over n, as long as n is a positive integer. So here we're going to look at a couple examples, and then we'll tackle part 2. So here I have the limit as x approaches c of x equals c. So here it's asking me for the limit of the quantity x cubed plus 4x squared minus 3 as x goes to c. So what we're going to look here is we're going to actually look at separating this into 3 different parts. So I'm looking here at separating it into the limit of x cubed, the limit of 4x squared, and minus the limit of x as c of 3. And so now, when I look at this, this is the power rule. So the power rule says, as long as n is a power, it's the cube of the limit. So here I have the limit. So this becomes c cubed. Plus, now I have a constant multiplier, so that's k times the limit, and I have the power. So that's going to be 4c squared minus 3. Now we're going to look at what happens when I actually put a specific value in here. So I have x is going to negative 2. So I have the limit of the square root of 4x squared minus 3 as x goes to 2. And so what I'm going to do is I'm actually going to plug in 2. For negative 2 squared minus 3. It actually you're going to have the root rule and the difference rule on there. So I'm going to come here, square root. This becomes 4 times 4 minus 3, which is the square root of 16 minus 3, which is the square root of 13. There's my limit as x goes to negative 2. So that's part one of the limits of the function.